Hello, and welcome to this lecture in my series on the satisfiability problem for fragments of first-order logic. My name is Pratt-Hartmann, and today I shall be talking about the Aristotelian syllogistic and some of its extensions. As usual in these lectures, I shall assume basic understanding of first-order logic and computational complexity theory, and I'll be going over the main ideas in the proofs I'll be discussing, but I won't list all the technical details. If you are interested in these, then I refer you to my book Fragments of First-Order Logic, which was published by Oxford University Press a couple of years ago. Chapter 2 deals with this topic today. Logical relationships involving the simplest quantifying assertions were first investigated in Aristotle's prior analytics. Let's have a look at an example. So suppose some artist is a beekeeper, every beekeeper is a carpenter, and every carpenter is a dentist. It follows that some artist is a dentist. That is, if the propositions above this horizontal line are true, then so is the proposition below the horizontal line. We ask, is there an algorithm for determining the validity of arguments involving such sentence forms? There's one technical detail I'd like to mention right at the beginning. We'll follow current logical practice in taking a sentence such as every beekeeper is a carpenter to be true if there are no beekeepers. In other words, every beekeeper is a carpenter does not entail that there are beekeepers, or indeed that there are carpenters. Similarly with every carpenter is a dentist. Aristotle and in more traditional logic, the opposite assumption is made, but we'll follow contemporary logical practice. That's a technical detail. It doesn't really change anything in the proofs that I'll be giving. So Aristotle, in effect, provided an answer to our problem. Is there an algorithm for determining the validity of arguments in such a fragment, by providing a list of valid syllogisms. A syllogism is an argument form with two premises and one conclusion. And you'll see that in these argument forms we have schematic letters standing for properties such as artist, beekeeper, carpenter, whatever you like. So here's the first inference rule. This is one of those that Aristotle listed. Every O is a P, every P is a Q. It therefore follows that every O is a Q. Here's another one. Some O is a P, every P is a Q. It therefore follows that some O is a Q. Now, by chaining syllogisms together, we can construct derivations. Consider the argument of the previous slide where I had the premises in blue. Some artist is a beekeeper, every beekeeper is a carpenter, every carpenter is a dentist, and again we have the conclusion in red here. If we substitute beekeeper for O, carpenter for P, and dentist for Q, we see that two of the premises match the premises of this syllogism, so we can infer the corresponding conclusion. Every beekeeper is a dentist. If now we consider the third premise, some artist is a beekeeper, we see that by substituting artist for O, beekeeper for P, and dentist for Q, we match the premises of this syllogism so we can infer the corresponding conclusion. In this case, some artist is a dentist. So by chaining syllogisms together, we've shown the validity of the argument in the example of the previous slide. The question, of course, is can all instances of valid arguments be reconstructed in this way? And it turns out that with a little goodwill, Aristotle's syllogisms suffice to do exactly this. I'll explain later what I mean by with a little goodwill. There are some corner cases which Aristotle wouldn't have considered sensible, but which from a modern point of view we do. But these are really just, as I say, corner cases. Essentially, Aristotle had a complete system. So let's get clear about the language we're dealing with first. The classical syllogistic consists of sentences of the following forms. Every P is a Q, some P is a Q, no P is a Q, some P is not a Q. And these can be formalised in first-order logic in the obvious way. Here I use the plus or minus symbol to mean either negated or not negated. So if this symbol here is q of x, then that says every p is a q. If this symbol is not q of x, then that means that no p is a q, and similarly for these cases as well. So we have a fragment of first-order logic, a collection of formulas of first-order logic, but not the whole of first-order logic. And we'll call this fragment S, S for syllogistic, I suppose. Now, formalising things in this way reveals some missing possibilities. You'll notice from the previous slide that we can negate this subformula q of x, but we couldn't negate p of x. Well, what happens if we can? So one might consider the formulas all non-p's are q's, or some non-p's are not q's. These formulas are not equivalent to any formulas in the classical syllogistic as I just defined it. And you might say, well, why can't we have such formulas? And the answer is no reason at all. We can render them in English as every non-p is a q, some non-p is not a q. It's not exactly English as she is spoken, but it seems to be fairly comprehensible. And certainly from a logical point of view, this makes perfect sense. So we'll define the extended classical syllogistic, and I'll denote that by S plus, to be the classical syllogistic together with formulas of this form here. So we can have not p as the first argument of these formulas. Okay, so again, we can ask, is there an algorithm, a method for determining validity of arguments in the extended classical syllogistic? Now, in either the classical syllogistic or its extended variant, variables convey no information and can therefore be deleted. So here are two examples of sentences in this fragment. I've written the English glosses and the actual formulas below. So here are the variables, which I've highlighted in blue here. And I think you can see that, well, they don't contain any information. We might as well get rid of them. You can always put them back, but there's no information loss here. And of course, we can just move things up to compress things in the usual way. Now, in addition, you'll see that Boolean connectives, the Boolean connectives implies and are also, well, they're redundant because they're determined by the preceding quantifiers. So we may as well get rid of them and replace them with a comma. And finally, we'll write negations in a more compact way. Just a bit more convenient. Instead of writing not dentist, I'll write dentist with a bar over it. And that's it. So I'll use this more compact notation for formulas of the syllogistic and also the extended syllogistic. It should be fairly obvious how it works. It's just it avoids a lot of the fuss of the full predicate notation, predicate calculus notation, which we don't really need in this simple case. So, henceforth, we'll refer to unary or one-place predicates, some things like P or Q, or the things that stand for properties, artist, beekeeper, carpenter. We'll refer to these as unary atoms, and we'll refer to either of the expressions P or P bar, where P is a unary predicate or a unary atom, as a unary literal. So unary atom is just a one-place predicate, and a unary literal is either a one-place predicate or the same thing with a bar over it. And we read P bar as not P, or non-P. We call literals of the form P positive and literals of the form P bar negative. Now, I will usually use the letters OP and Q to range over unary atoms, and LM and occasionally N to range over unary literals. And doing so, we can define the formulas of the classical syllogistic to simply be expressions of these forms, all P's are L's, and some P's are L's. And likewise, we can define the formulas of the extended classical syllogistic to be expressions of the forms all L's are M's and some L's are M's. Remember, L and M are literals, either unary atoms or unary atoms with bars over them, and P is a unary atom here. So if L is a negative literal, it has a negation defined in the obvious way. We'll define L bar to be the corresponding positive literal. So you remove the bar. And if we do that, we see that we have the following logical equivalences. Clearly, some L's are M's is the same as some M's are L's. And also, equally clearly, all L's are M's is the same as all non-M's are non-L's. Scratch your head a little bit for a couple of minutes, you'll realise that those are equivalent pairs. And in that case, we may as well regard these forms as interchangeable. So I'll switch between forms as and when the fancy takes me. A slightly different idea. If you look at the formulas in the classical syllogistic, all P's are L's and some P's are not L's, we see that they're equivalent to each other's negation. And if some P's are not L's is true exactly when all P's are L's are false. Is false. So we effectively have negation in the classical syllogistic, and similarly for the extended classical syllogistic. I mean, all P's are L's and all P bars are L's and some P bars are not L's, again, each other equivalent to each other's negation. So effectively, both the classical syllogistic and the extended classical syllogistic are closed under negation. Both fragments are closed under negation. Accordingly, if phi is a sentence of a universal sentence, i.e. one of the form all L's are M's, L and M are literals, we'll write phi bar to be some L's are not M's. In other words, the negation of phi. And if phi is the existential formula some L's are M's, we'll write phi bar to be the formula all L's are not M's. So we can read phi bar as not phi. In the language of the syllogistic, classical syllogistic, and its extended variant, we don't actually have the negation symbol, but we can negate formulas by carrying out these obvious syntactic changes. So effectively, these languages are closed under negation, and we'll write phi bar for the effective negation of phi in either of these languages. The semantics of these languages are just the usual semantics of first-order logic. And the notions of satisfiability and valid entailment are, of course, carried over in the usual way. Just as a reminder, a set of formulas is big phi is satisfiable just in case there is some structure in which they're all true, i.e. some structure A such that A models big phi. Of course, in the fragment we're talking about all formulas are by definition closed. There are no free variables anywhere here. Similarly, a set of premises big phi entails the conclusion psi just in case all structures in which all the formulas in big phi are true are ones in which psi is true. In other words, A models phi implies A models psi. Hence, it's easy to see that a set of formulas big phi entails a formula psi just in case the set of formulas big phi together with the negation of psi, that is psi bar, is not satisfiable. That's simply the usual duality regarding entailment and satisfiability. So if we want to test for validity of arguments, it's just as good to be able to, we can just test for satisfiability of sets of sentences. That's just as good. So what we seek is an algorithmic solution to the satisfiability problem for the classical syllogistic and the extended classical syllogistic. So the satisfiability problem, remember it as follows. You are given a finite set of formulas in the fragment in question, and you return yes if that set of formulas is satisfiable, no otherwise. Similarly for the extended classical syllogistic. It's exactly the same problem. So we want to know, if you give me a set of formulas in either language, is there a method that I can use to determine satisfiability? And that will tell us everything we need. Now, let's look, before we address these questions, let's look a little bit beyond. The classical syllogistic gives us absolutely no purchase on essentially relational arguments. And consider the following example. Every beekeeper admires some artist. Every artist admires some artist admires no beekeeper. Therefore, some artist is not a beekeeper. Actually, you have to think a little bit to see that this is a valid argument. Let's have a look. Let's look at the second premise first. Some artist admires no beekeeper. Well, let's take such an artist, call him Fred. Okay? Fred is an artist who admires no beekeeper. Now, if Fred is not a beekeeper, the conclusion's true because we've got some artist who's not a beekeeper. So we may as well suppose that Fred is a beekeeper. This is Fred, by the way. Okay, so Fred's an artist and we may as well suppose he's a beekeeper. Otherwise, there's no work to do. But just a moment, the first premise says every beekeeper admires some artist, so let's pick an artist whom Fred admires. But Fred doesn't admire any beekeeper at all. So this artist whom Fred admires can't be a beekeeper. So we have another artist here, and he is definitely not a beekeeper. So the conclusion follows either way. So clearly this argument can be formalised in first-order logic. Here's the first-order formalisation if you want to have a look at it. Pause the video. It's completely straightforward and uncontroversial, so I'll just pass over that now. So let's define the relational syllogistic, and I'll denote this R, to be the set of formulas which are either in the classical syllogistic or which have any of the following forms. All P's are related by R or related by not R to all Q's. All P's are related by R or related by not R to some Q's. Some P's are related by R, related by not R to all Q's. Some P's are related by R, related by not R to some Q's. So we have these sentence forms as well. Again, plus or minus is either the formula without the negation or the formula with the negation. So it's the usual sense. Okay, so that's the relational syllogistic. It's very important here that this is an extension of the classical syllogistic, not the extended classical syllogistic. So in this fragment, you don't have sentences like all non-A's are B's. So that's not those aren't in this fragment. We just extend the classical syllogistic with these relational forms here. Again, the variables and Boolean operators carry no information and so may be omitted and the formula's closed up. So we can write these formulas, so we just get rid of the variables and all the associated brackets, close them up, and the Boolean operators again can be inferred from the nearest quantifier, or the nearest dominating quantifier, I should say. So we can write these formulas in this form. So if we use the plus variant here, that says every P R's every Q. If you use the minus variant, that's no P R's any Q. And similarly for all these forms here. Okay, good. So that's the relational syllogistic. Again, remember we write, we can also write not R as R bar, so as in the usual way. So if we look at the argument that the example that I just gave, every artist admires some beekeeper admires no artist, therefore some beekeeper is not an artist. I can write it in this way like that. And such arguments, syllogistic looking like arguments, but with relational terms, attracted the attention of various logicians in later centuries, particularly Augustus de Morgan, who clearly saw that the Aristotelian syllogistic wasn't adequate to account for the validity of such arguments. So note that expressions such as all PR, where R is a binary predicate, and similarly all PR bar, some PR R and some PR bar, denote properties of objects. So this is an expression like admires all beekeepers, or this is fails to admire some artist. Those kinds of expressions here. So they denote properties of objects, just like literals. unary literals. So we'll call such expressions, as well as all unary literals, C terms. C for concept, I suppose. So a C term is either a literal, a unary literal, that is a unary atom or a unary atom with a bar over it, or one of these expressions here, and C terms denote properties of objects. So if we use P and Q, as usual, to range over unary atoms, and C to range over C terms, we may define the formulas of the relational syllogistic excuse me, to be expressions of the form some P's are C's and all P's are C's. So C is a C term, that includes unary atoms, unary atoms with bars over, so all unary literals, and also all of these complex terms here, like admires every artist and so on. So expressions of these forms are the formulas of the relational syllogistic. And again, we can ask, is there an algorithm for determining validity in this larger logic? Now, as with the classical syllogistic, the formalisation of the relational syllogistic suggests some missing possibilities. R cannot express sentences like this: every P R's some non-Q, or some non-P R's no non-Q. So we can extend the relational syllogistic just as we did for the classical syllogistic. Say that an E term, I don't know why I call them E terms, but I've got to call them something. An E term is either a literal or any expression of this form. So R's all L's, fails to R any L's, R's some L, fails to R some L, where L is now a literal. It would be P or P bar. And using L to range over literals and E to range over E terms, we can denote the formulas of the extended relational syllogistic, and I'll call that R plus, to be expressions of the form some L's are E's, I beg your pardon, or all L's are E's, where L is a literal, a unary literal, and E is an E term. Remember, an E term is either a unary literal, one of these complex properties of objects here. So the extended relational syllogistic stands in the same relation to the relational syllogistic as the extended classical syllogistic does to the classical syllogistic. That is, we can simply allow noun level negation. We can talk about non-P's and non-Q's and things like that. And again, we ask the same question: is there a algorithm for determining the satisfiability of sets of sentences in this fragment? So we have actually three extensions of the classical syllogistic. Classical syllogistic, the extended classical syllogistic, where we have things like, where we have noun level negation, we can talk about non-B's. The relational syllogistic, where we can say things like every artist admires some beekeeper, and we have the extended classical syllogistic, which is a combination of both. And we want to know, can we determine the validity of arguments or the satisfiability of sets of formulas? Now, I'm going to start with the fragment S+, the extended classical syllogistic, because this is probably the simplest and most uniform one to analyse. So let phi be a set of universal formulas in the extended classical syllogistic. So universal formulas, remember, are those of the form all. So all L's are M's, where L and M are literals. Now, I'm going to write L arrow subscript phi M if phi contains the formula all L's are M's. And I'm going to write L double arrow, again subscript phi M, for the reflexive transitive closure of this relation. So what that means, so this double arrow means that there's a chain of universal formulas in phi leading from L to M in the obvious sense. Now, since all L's are M's and all non-M's are non-L's are regarded as the same formula, then these paths, I'll talk about a path from L to M in the obvious sense, these paths are what you might call skew reversible. Suppose we have a path leading from L1 to LK. In other words, phi contains the formula all L1s are L2s. It contains all L2s are L3s, and so on all the way up to all LK minus 1s are LKs. Well, in that case, since these formulas, all L's are M's is the same as all non-L's, non-M's are non-L's, we can reverse this path. There's a path from all non-LKs there's a path from LK bar to L1 bar. Let's say that right. I mean, these two things are the same condition because these formulas are regarded as the same. So I'll allow myself to skew reverse paths in the obvious way, in the sequel. Okay, so good. Let's put that idea on the stack, and of course we can. So L, I've just said this. L, there's a path from L to M, just in case there's a path from M bar to L bar. Obviously, if there's a path from L to M, then phi entails all L's or M's because there's a chain of entailments starting with L and ending with M, so it must follow that all L's or M's from the formulas in phi. Okay. Now, having established that notation, let phi be a set of universal formulas in the extended classical syllogistic, and let psi be a set of existential formulas in the extended classical syllogistic. What we're now going to do is give an algorithm for checking the unsatisfiability of phi together with psi. So I've got this is just a set of formulas in the extended classical syllogistic, and I've split it up here into universal and existential formulas, just so we can see better what's going on. And this algorithm will determine whether this set it will answer yes if the set is unsatisfiable, no if the set is satisfiable. So it's the reversal of the problem we want, but that's good enough because we can just reverse the answer once we've got it. Okay, so call it ND unsat. What does it do? It goes through all of the existential formulas in psi in turn. And then for any such existential formula, some L's or M's, it asks, is there a path in the universal formulas from L to M bar? Or is there a path from L to L bar? Or is there a path from M to M bar? In any of these cases, we'll return yes, unsatisfiable. If none of these checks return yes, then we go through every unary atom mentioned in the whole set, phi. And if there is a path from O to O bar, and also a path from O bar to O, then again we return yes, unsatisfiable. Otherwise, if none of these checks work out, then we return no, in other words, not unsatisfiable, in other words, satisfiable. So remember, this is an algorithm to check unsatisfiability. And the first thing to do is to establish that this algorithm actually works. So let phi be a set of universal formulas in the extended classical syllogistic, psi a set of existential formulas in the extended classical syllogistic. Then I claim phi union psi is unsatisfiable if and only if this algorithm returns yes. Now, the if direction is pretty straightforward. So here's the algorithm for reference, and let's look at the only possible cases in which it could return yes. So we have a return yes here and a return yes here. So so the first possible case is that one of these conditions here, one of these disjuncts is satisfied for some existential formula here. Okay, so we have an existential formula, some L's are M's in psi, and we have a path from L, let's say, to M bar. Well, if there's a path from L to M bar in phi, the universal formulas, then those universal formulas entail that all L's, I should say, let me say it easily, that no L's are M's. All L's are non-M's. So no structure satisfies phi together with the formula some L's are M's, so clearly phi is not satisfiable. And exactly similar considerations occur if any of these conditions obtain, if either of these two conditions obtain as well. You can easily see that no structure can satisfy, no model can satisfy the universal formulas phi together with the relevant existential formula. So clearly, if the algorithm returns yes because of this line, then the set is unsatisfiable, so that's all fine. What if the algorithm returns yes because of this line? Well, in that case, this red condition must also be satisfied. There must be a unary atom O such that O bar is reachable from O and O is reachable from O bar. But in that case, if O bar is reachable from O, that means there are no O's in any model of phi. It means that because clearly then O entails not O bar, O entails O bar, so all O's are not O bars. In other words, there aren't any O's. And similarly, if O bar entails O, if there's a path from O bar to O, then phi entails that all non-O's are O's. In other words, everything's an O. But as usual in logic, we always assume that domains are non-empty. So there must be some object in the domain. There must be at least one object existing. And if this condition holds, then that object must be a non-O. And if this condition obtains, that object must be an O. And that's impossible. So there are no models of phi. So clearly, in either case where the algorithm returns yes, the set phi together with psi is unsatisfiable. Now let's look at the if direction, which is a little bit more difficult. We must show that if the conditions on returning yes are never triggered, right? Remember that the algorithm returns yes only if these blue conditions are triggered or this red condition here is triggered. If these conditions are never triggered, then we must show that the set phi union psi is satisfiable. In other words, to show this, of course, we have to build a model. So let's do that. For simplicity, we'll consider first the case where psi, the set of existential formulas, contains just one formula. There's just one existential formula. Some L's are M's. All the other formulas are universal. Okay, so what we're going to do is we'll build a model of our universal formulas together with this single existential formula, some L's are M's, and that model will have a one-element domain. So it's a very simple model. There'll just be one element in the domain of this model. Call that A. We'll call the model Fraktur A, and we'll define it. So how do we define A? Well, we have to say which unary literals the element little a satisfies. So let's specify which literals it satisfies. In particular, we'll specify which unary atoms it satisfies. Remember, a unary atom is a unary predicate. So we'll take A, little a, to satisfy a unary literal n, and I'm using n to range over unary literals here, not integers. We'll take A to satisfy a unary literal n, just in case there's a path from L to n, or a path from M to n in the universal formulas phi. Now, does this even make sense? We have to be a little bit careful because we don't want to assign to the object A the literal O and also the literal O bar, because that wouldn't make sense. I mean, either it satisfies O or it satisfies O bar. As long as we don't try to assign it competing literals, we'll get a perfectly sensible model here. But I claim that we could never try to assign, if we assign literals to element A as just suggested, if there's a path from either L to that literal or M to that literal, then we can never try to assign competing literals. Because suppose there were a path from L to O and a path, let's say, from M to O bar. Well, remember that we can skew reverse paths, so we can write this second path here as a path from O to M bar. Well, then we've got a path from L to O and a path from O to M bar, so putting these two paths together, we have a path from L to M bar. But just a moment, if there's a path from L to M bar, our algorithm will return yes, because we'll have an existential formula, some L's or M's in our set, and a path from L to M bar. And so it's clear then that the algorithm could not have returned no. We're assuming, remember, that the algorithm returns no. We have to build a model. And this is a proposal for building a model, the second point here. And I've just shown that if we assign literals in that way, we will never try to assign opposite literals to our element A. And so the model will be perfectly legitimate. And when we do that, remember, we'll have made this existential formula true. Of course, clearly there's a path from L to itself, trivially, and a path from M to itself, trivially. So this element A will be assigned both the literals L and M, so it will certainly make this formula true in our model. We'll have made this formula true, the existential formula, and because of the way we've assigned literals to formulas, it's clear that we can't have violated any universal formulas in phi, because if we have a formula in phi which says all, let's say all m's are m primes, another letter, all n's are n primes, right? Something like that. If we have n in, if we assign n to the element A, we'll assign also n prime to the element A, just because of the way in which we've assigned literals to A here. So all of our universal formulas will be made true. So it looks like we're home. Looks like we've got a model of our existential formula and our universal formulas. Well, not quite. Right. The problem is that, so certainly we've made the existential formula true and we've violated no universal formulas. However, there may be unary atoms O for which it's not yet been decided whether A satisfies O or O bar. In that case, we have to be a little bit careful. We have to decide, because we have to think, do we assign a literal O to A, or do we assign O bar to A? It's not clear. And here's what we'll do. If O bar is reachable from O, we'll take A to satisfy any literal n such that n is reachable from O. Otherwise, we'll take A to satisfy any literal n such that n is reachable from O bar. And using an exactly similar argument to the one of the previous slide, we can show that this cannot lead to assigning both n and n bar to our element A, where n is a unary literal, since otherwise we would then have, it's easy to see that then we would have both conditions O bar is reachable from O and O is reachable from O bar. So I'll leave people to just reconstruct that argument there, but it proceeds in exactly the same way as the argument on the previous slide. We have to use the fact that chains of implications can be skew reversed in the way I showed before. So we know from the algorithm that if we ever have the condition O bar is reachable from O and O is reachable from O bar, if that condition ever obtains, then we'll return yes. In other words, we'll say the formula is unsatisfiable. So if the algorithm says the formula is satisfiable, if the algorithm returns no, this condition never obtains. And if that condition never obtains, then this method of assigning unassigned literals to our element A, where's A? Our element little a in the structure will never lead to our trying to assign competing literals to A. So we'll have a sensible model. We'll have completely defined the model because all unary literals will be accounted for. We can just keep going until we've defined everything. And we will have made sure that this existential formula exists Lm is true, and we won't have violated any universal formulas, so we'll have a model of our universal formulas together with our single existential formula. Remember, we're assuming then here that psi is a single existential formula. There exists Lm. Okay, so that algorithm will, in that case, never return no unless the set of formulas in question is satisfiable. Now, the only case we have to consider, the only thing we have to do now is to look at the more general case where we have more than one existential formula. So suppose that big psi consists of the existential formulas phi1 to psi1 to psi e. Okay, so what does the algorithm do? Well, it says go through all the existentials in turn and do the checks that I just described. Of course, these checks on the unary atoms are independent of the existential formula. So we do this check for all the existential formulas, and of course we do the check on the unary atoms here. That's unaffected as before. And so if any of these checks comes out, if any of these conditions is satisfied, we return yes, unsatisfiable. If we say that the algorithm is satisfiable, then all of these all of these conditions must have failed. In other words, we must be able to build a model A1 of the universal formulas together with the first existential, A2 of the universal formulas together with the second existential, all the way up to AE, which is a model of the universal formulas together with the eth, or final existential formula. So all these models must exist separately by the argument I've just given. And how do we build an argument of everything together? Well, we just take A to be the disjoint union of these models, and it should be obvious then that this large model A is the union of phi together with psi, and that completes the correctness proof for this argument. We've shown that if for this algorithm, I should say, so if the algorithm returns yes, then clearly the formula set is unsatisfiable, and if it returns no, then we can construct a model of that formula set, so the formula set is satisfiable. Now, it's worth considering what happens when phi and psi are all contained in the fragment S rather than S plus. Remember, S is the classical syllogistic, S plus is the extended classical syllogistic. It turns out, I mean, clearly the same argument, well, the same algorithm must work because the extended classical syllogistic contains the classical syllogistic, so there's nothing wrong with the argument, we can just run it. It will certainly work, but you may notice that the grayed out lines, the tests in the grayed out lines can never succeed. So we can simply omit lines 5, 6 and 7 because the restrictions on the classical syllogistic, which says that you can't have a negated first argument of the formula, mean that these paths, these two conditions can never hold. It's worth thinking what this all means in terms of building models. Recall that when we showed the correctness of this algorithm, we supposed, for simplicity, that psi consisted of a single existential formula, and we showed that if the algorithm returns the answer no, then we can build a model of that existential formula together with all the universal formulas. And we did that by taking an element, a single element, A, and we assigned A to satisfy every literal n such that either n is reachable from L or n is reachable from M. And when we did so, we pointed out that that would be sufficient to secure the truth of the existential formula and violate none of the universal formulas. But we also pointed out that there would be undecided unary atoms. I mean, there might be unary atoms O for which we've not decided yet whether our element A satisfies O or its negation. Now, when we're working in the classical syllogistic, we have a very simple solution here. We can just say the element A doesn't satisfy any of these undecided atoms. When we do that, because we're in the classical syllogistic, we'll never violate any universal formulas. So we have a very simple way of completing the model, and we don't need to run this grayed out check here. This turns out to be extremely important, and we'll see why when we come to look at the relational fashions of these arguments. But for now, we can sort of put that to one side. This algorithm, without the grayed out material, works perfectly well for the extended classical syllogistic, and you don't need the grayed out material if you're working within the classical syllogistic. A word about complexity. It's easy to see that the algorithm runs in quadratic time. In fact, we can do a little bit better. Recall that we write L double arrows subscript phi m, just in case there's a path m is reachable from L along links of universal formulas occurring in big phi. So in effect, the formulas phi together with psi define a directed graph. The vertices of this graph are the unary atoms mentioned in the formulas together with their negations. And there is an edge from a literal L to a literal M, just in case the formula LM, or equivalently, just in case the formula all L's are M's, or equivalently all non-M's are non-L's, is in the universal formulas. In other words, what the algorithm, so L double arrows phi m means that there's a path in this directed graph from L to M. So what this algorithm asks us to do is to perform a series of reachability queries for directed graphs. But reachability in directed graphs is a problem well known to be in n-log space, and so it follows easily that the unsatisfiability problem for S plus, the extended classical syllogistic, is in n-log space. According to the Immermann-Selim-Cheyne theorem, n-log space is equal to co-n-log space. Hence, the unsatisfiability problem for S plus is in co-n-log space, hence the satisfiability problem is in n-log space. And so we have proved this theorem. So we now know the complexity of the satisfiability problem for the classical syllogistic. It's possible to prove a matching lower bound for the classical syllogistic, the smaller language, by reduction from the well-known reachability problem, which is in directed graphs, which is known to be n-log space hard, and it follows therefore that the satisfiability problem for the classical syllogistic and the extended classical syllogistic are both n-log space complete. I won't give the details of the lower bound in this lecture today. Now let's consider the satisfiability problem for the relational syllogistic R. Remember, the relational syllogistic is an extension of the classical syllogistic. It is not an extension of the extended classical syllogistic. That is, we don't, in the relational syllogistic, we have sentences like every artist admires some beekeeper. We don't have sentences like every non-artist is a beekeeper. It turns out that a very similar treatment can be given as in the case of the extended classical syllogistic. For any finite set R of R formulas, phi, we can construct a directed graph, G phi, such that determining the unsatisfiability of phi corresponds to executing a collection of reachability queries on this directed graph, very much as we did with the extended classical syllogistic. It follows that the satisfiability problem for the relational syllogistic is in n-log space, and since the relational syllogistic includes the classical syllogistic, the lower bound for the latter still applies, and therefore the satisfiability problem for the relational syllogistic is n-log space complete. There is, however, an important difference between the procedures for the extended classical syllogistic and the relational syllogistic. In the case of the extended classical syllogistic, the directed graph which we constructed had vertices labelled with unary literal. So we thought of the vertices as unary literal satisfied by some fixed object. When we construct a directed graph for the relational syllogistic, we have to think of the vertices as standing for individuals, objects of the domain, and those vertices are labelled with the collection of unary atoms which those individuals are taken to satisfy. So although that seems a technical difference, it betrays an important fact. When we try to apply the same technique to the extended relational syllogistic, that is the relational syllogistic with noun level negation, so including sentences like every non-artist admires some non-beekeeper, that construction fails. And it must fail for the following reason. It turns out that it can be proved that the satisfiability problem for the extended relational syllogistic is exp-time complete. Thus, no polynomial size reduction to a directed graph searching procedure is possible for the extended relational syllogistic. So if you have the classical syllogistic, you can solve the satisfiability problem. The extended classical syllogistic can solve the satisfiability problem in the satisfiability problem is in n-log space, and the same is true of the relational syllogistic. And again, it's a matter of in both cases you show this by reduction to a graph searching problem. If, however, you try to extend both with relations and noun level negation, and look at the extended relational syllogistic, fragment where you have things like all non-artists admire some non-beekeeper, then the resulting satisfiability problem is exp-time complete, and so cannot be solved by reduction to a polynomial size graph searching problem. Now, we mentioned earlier that Aristotle provided a solution to the problem of determining valid arguments in the classical syllogistic by listing valid syllogisms, so syllogisms like this. So in the more compact syntax that we're using, we can write syllogisms in the following form. All O's are P's, all P's are Q's, therefore all O's are Q's. It's clearly a valid argument schema. Or again, some O's are P's, all P's are Q's, therefore some O's are Q's. Again, this is clearly valid. We'd like a system of rules able to derive all valid arguments. So we know we've got an algorithm to do it. Can we construct arguments in the traditional classical sense? So the idea is, of course, we chain these syllogisms together to construct derivations. So here's our original argument. Every beekeeper is a carpenter, every artist is a dentist, some artist is a beekeeper, and it follows by a chain of two deductions that some artist is a dentist, and here's the same argument but in our notation, in our compact notation here. So can we devise a system of inference rules to do this? Well, suppose we have a finite set of rules, call this set X. So we can label the rules some way we like, but let's suppose that the rules look just like the syllogisms that we just listed. Of course, we allow any number of premises. We could have an argument scheme, a rule with 57 premises in a single conclusion. That would be perfectly fine, just a finite number. And we'll write big phi syntactically entails psi subscript x if the formula psi can be derived from the set of premises big phi via the inference rules in the set X. So we're asking, can we find a set of rules, big X, let's say for the extended classical syllogistic, such that big X is sound, in other words, if something is derivable from phi, then phi entails it, and complete. If phi entails something, then that's derivable from phi. So that's what we would like to know, and I suppose in some sense that's a question Aristotle asked. We can do that. Here's a collection of rules for the fragment, the extended classical syllogistic. So the first two rules are just basically generalizations of syllogisms, or groupings really of syllogisms, which Aristotle recognized. Again, I'm simplifying things slightly because remember, Aristotle used existential presupposition. He took all A's or B's to imply that there were A's. So this is a slightly different logic, but that's really just a technical difference, and we can even account for that if we want. Modulo that simplification, these are just the familiar Aristotelian syllogisms, right? Some L's are N's, all L's are M's, therefore some M's are N's. All L's are M's, all M's are N's, therefore all L's are N's. So that's basically a generalization of Darii, and that's a generalization of Barbara. Aristotle's syllogisms had traditional medieval mnemonics, so that's Darii and Barbara are just some of them. Okay, so here are our first two rules. Perfectly good rule schemata for our fragment S plus. Remember, L, M, and N are literals, unary literals. So we need a few rules to handle corner cases, and these are the rules which don't occur in Aristotelian syllogistics. I mean, they wouldn't really make a great deal of sense to Aristotle. All L's are non-L's implies all L's are M's, right? Because if all L's are non-L's, then there aren't any L's, so trivially all L's are M's. From no premises at all, you can infer that all L's are L's, and if some L's are M's, then some L's are L's. Well, this is all very trivial, but you do need such rules formally. And finally, we have a couple of rules dealing with absurdity and vacuous quantification. Again, this wouldn't have made any sense to Aristotle. If you have a formula psi and its negation, remember you can effectively negate formulas in these languages, then absolutely anything follows from that. So we have the so-called rule of ex falso quod libet, which I've slightly confusingly perhaps labelled X here. And we have this rule which I've labelled N, which has to do with the fact that domains are assumed to be non-empty. If no L's are L, if all non-L's are L's, that means everything is an L. In other words, there are no non-L's. And it therefore follows that something is an L because of the assumption of non-empty domains. We always assume in logic now that domains are non-empty. It's a bit simpler that way. So we need that rule as well. So let's call the system S plus. That's I don't know, non-calligraphic sans serif S plus. We'll use that as the name for the collection of rules I've just given. Let's go back. Classical syllogisms, these corner case things, and these things to handle absurdity and empty domains. Now, by adapting the proof that S plus is in n-log space, that the extended classical syllogistic can be decided for satisfiability, say that again. By adapting the proof that the satisfiability problem for the extended classical syllogistic is in n-log space, which I went through in detail, you can actually show that the set of rules that I've just given is sound and complete for S plus. So it's easy to show that they're sound, and the proof that they're complete involves model constructions very, very similar. I mean, you really basically just repeating the proof of the correctness of the algorithm that I went through, just slightly changing a few things, slightly different formulation, but it's essentially the same proof. And that gives you a completeness proof. So we have a sound and complete set of rules for the extended classical syllogistic. We can give a similar set for the ordinary classical syllogistic. That's perfectly straightforward. So we don't need to stray into the extended classical syllogistic if we want to give proofs of validity of arguments. Can we write a sound and complete set of syllogistic rules for the relational syllogistic or even the extended relational syllogistic? For example, can we have rules that allow us to demonstrate the validity of the argument that I gave as an example before? Every artist admires some beekeeper admires no artist, therefore some beekeeper is not an artist. Might think that we could write some rules. So here are some examples. Here's a candidate rule. If every P is related by T to every O, and some O is a Q, then every P is related by T to some Q. Or again, if every p is related by t to every o, and some q is an o, it follows that every p is related by t to every q. And there's a similar one where you have an existential here, universal here. Can leave people to read through these rules. These rules are clearly valid, and we might ask, well, is there a complete set of rules which will work for the relational syllogistic? Surprisingly, the answer is that there isn't, and I can prove this using a fairly simple argument. So let's have a look. So the theorem is that there exists no finite set X of syllogistic rules in the relational syllogistic, such that the derivation system based on that system of rules is both sound and complete. And the way I'm going to do this is by defining a large set, big gamma, of formulas. Now, gamma will actually be an infinite set, but that's okay. I will take P1 to Pn to be distinct unary atoms. So artist, beekeeper, carpenter, just suppose that we've got n of them. And I'll take R to be a binary atom, like loves or admires or hates or something like that. Now, my set gamma will contain the following formulas. It will contain the formula, every pi is related by R to some pi plus 1, for I ranges from 1 to n minus 1. So I've diagrammed that here. Every pi is related by R to some p2, every p2 is related by R to some p3, and so on, all the way up to pn. So these arrows indicate the relation R. The next formula in gamma will be the formula which says that all p1s are related to all pn's by R. So if you've got a p1 here and you've got a pn here, then they're definitely related by R. And I've written that in red. This is a universal quantifier here, note. I mean, if there might, remember that there might not be any p1s or there might not be any pn's, as far as we know. And this formula here says that the collection, the next formulas in gamma are all formulas of the form all p's are p's. And this is infinite, right? So just get any formula at all for any unary atom, all p's are p's. Okay, and finally, we'll have formulas saying that the pi's, remember, P1 to Pn are just these unary atoms which I've distinguished here, related by these formulas in gamma. And I'll say that for each of them, I'll say that there are no pi's or pj's where I and j are distinct. So no p1s are p2s, no p1s are p3s, or denote disjoint sets of objects. Okay, so those are my formulas in big gamma. It's just a set of formulas in the relational syllogistic. Now, so big gamma contains the formulas all pi's are related by R to some pi plus 1, and all p1s are related by R to all pn's. Now, let little gamma be the formula all p1s are related by R to some pn's. Now, I claim that big gamma implies little gamma. Why? Well, if there are no p1s, little gamma is certainly true. So suppose there are p1s. Since all p1s are related by R to some p2s, there must be some p2s. Since all p2s are related by R to some p3, there must be p3s, and so on and so forth. Therefore, there must be pn's. And since all p1s are related by R to all pn's, and there must be p1s and pn's, then all p1s are related by R to some pn's, because there must be pn's. Okay, so clearly big gamma implies little gamma. Observe also that little gamma is not one of the formulas of gamma, big gamma. Big gamma is a set of formulas. Let's go back to the slide where it's defined. It's a big set of formulas here. Little gamma isn't one of them. So, little gamma is entailed by big gamma, but it is not a member of big gamma. And we show that provided n minus 1, see n can be any number here, n is just a number, n is just some number. We show that provided n minus 1 is greater than the maximum number of antecedents occurring in any rule of x, then big gamma does not entail gamma using the rules of x. So we're supposing now that big X is some system of rules, some finite set of syllogism-like rules for the relational syllogistic. I gave some potential examples on an earlier slide. So we suppose that we have a finite set of such rules that enable us to determine, enable us to derive any valid argument in the obvious way. That set of rules, if it's finite, every such rule has a particular number of premises, and we can take the maximum number of premises over all such rules, provided the set of rules is finite. That's a general assumption, of course. And we're going to suppose now that n minus 1 is greater than the maximum number of antecedents of premises occurring in any of the rules of x. So let's see why, in that case, big gamma cannot be used to derive little gamma. Well, suppose I is between 1 and n minus 1. I'm going to define delta I to be the set gamma, but with this formula removed. Remember, big gamma contains all the formulas. All P1s are related by R to some P2, all P2s are related by R to some P3, and so on all the way up to all Pn minus 1s are related by R to Pn. And I'm going to remove the ith of the ith such formula from gamma, and I'll call the result delta I. So delta I is slightly smaller than gamma. Now, by considering the various forms of our formula in turn, what we can show is the following. If phi is any formula of R, and delta I entails phi, in other words, every model of delta I is a model of phi, then phi must be a formula of gamma. Okay, so we go through all possible forms of formulas. There's only a finite collection of formula forms in R. And we show that if, you can think of it contrapositively, if that formula is not a member of the set big gamma, then we can build a model, not of big gamma and the negation of the formula, but we can build a model of delta I and the negation of that formula. In other words, we can violate this implication. And that's just a rather straightforward and slightly boring check. Okay, so now we can reason as follows. Suppose some rule in X is applied to the formulas of big gamma, and that yields some consequent delta. So we start off with the formulas big gamma. We want to be able to derive little gamma. We apply some rule to the formulas of gamma, and that yields some of big gamma, and that yields some consequent little delta. Now, the rule, by assumption, has at most n minus 1 antecedents. So it must omit one of these formulas, at least one. Therefore, the antecedents of this rule must be contained within some delta I. But if the rule is valid, delta I must entail the conclusion, and therefore that conclusion must be in big gamma. Since the rule is, we assume that the rules are sound, since the antecedents of any such rule must be contained within some delta I, those antecedents must entail delta. But then delta must be a member of gamma by this condition here, which I claim we can establish. It's just a simple matter of considering all possible cases. Okay, so what does this mean? It means that starting from the set gamma, the big gamma, we can't escape. All of the rules, any valid rule, which remember has at most, any valid rule with at most n-1 antecedents, won't enable us to deduce any formula which is not in big gamma. So, since little gamma is not in big gamma, we can never use valid rules with at most n-1 antecedents to escape from big gamma, so we can't deduce little gamma. And since the rule set has to have a fixed maximum number of antecedents, we can always choose n so that this condition that n is greater than the maximum number of antecedents in any rule, we can always choose n to be sufficiently large, and we will have a formula which is entailed by big gamma but not derivable from it using the rules we started with. Consider any formula of the form some p's are not p's. Such formulas occur in all of the syllogistic fragments we've considered. Clearly, any such formula is false in any model. We'll call such a formula an absurdity, and we'll denote any absurdity by the symbol bottom. A set of formulas phi is clearly satisfiable if and only if it does not imply an absurdity. Of course, if a set of formulas implies any absurdity, it implies every absurdity. Now let capital X be a finite set of rules for some syllogistic fragment. We'll say that the set of rules X is refutation complete if, whenever a set of formulas phi implies an absurdity, in other words, whenever it's unsatisfiable, then that set of formulas that can be used to derive, via the rules in X, an absurdity. In other words, a set of formulas is refutation, a set of rules, I beg your pardon, is refutation complete if, whenever a set of formulas is unsatisfiable, we can derive, using the rules in X, some absurdity. So, if X is sound and refutation complete, then phi entails psi if and only if phi together with the negation of phi can be used to derive, using the rules X, an absurdity. In other words, we can still determine the validity of arguments if we have a set of rules which is refutation complete. Refutation complete is computationally as good as completeness. Not the same thing, it's a weaker condition, but it's computationally just as good. So, determining whether phi together with the negation of psi entails an absurdity can be thought of as indirect reasoning. We assume the negation of the formula we want to prove, we derive a contradiction, and we apply the rule of reductio ad absurdum, discharging our additional assumption and inferring its negation. Rather surprisingly, given the last theorem we proved, it turns out that it does exist a finite set, let's say sans serif R, of syllogistic rules in the relational syllogistic, such that the derivation system based on those rules R is both sound and refutation complete. So we can't get completeness, but we can get refutation completeness, and computationally speaking, that's of course just as good. I should point out that we've already explained that there's an algorithm for determining validity in R in terms of searching graphs, so we might as well use that, and we don't really need a derivation system to determine satisfiability, but if we like derivations, then you can't quite have a sound and complete derivation set. This theorem says you can have a sound and refutation complete derivation set. The construction of such that the proof again involves a modification of the decidability of the proof that the satisfiability problem for the relation syllogistic is in n-log space. I won't go through the details. They're too complicated. On the other hand, when it comes to the extended relational syllogistic, that's the fragment where you can say things like all non-artists admire some non-beekeeper, even reductio ad absurdum is no help. We can prove the following theorem. There exists no finite set sans serif plus of syllogistic rules in the extended relational syllogistic such that the derivation system based on those rules is both sound and refutation complete. And in fact, this follows quite easily by complexity theoretic consideration. Any such system of rules would yield an easy polynomial time decision procedure for the satisfiability problem in question. But it's known that the satisfiability problem for the extended relational syllogistic is x per time hard, and it is also known that x per time is not equal to p time. Therefore, there does not exist a finite set of syllogistic rules in the extended classical syllogistic, which is both sound and refutation complete. So let's summarize. In this lecture, we've examined the Aristotelian syllogistic together with three simple extensions. The extended classical syllogistic, so that's where you can say things like all non-artists are beekeepers. The relational syllogistic, where you can say things like all artists admire some beekeepers, and the extended relational syllogistic, where you can say things like all non-artists admire some beekeeper, or even some non-beekeeper if you like. The satisfiability problems for the classical syllogistic, the extended classical syllogistic, and the relational syllogistic are n-log space complete. The satisfiability problem for the extended relational syllogistic is x per time complete. There are sound and complete syllogistic systems for the classical syllogistic and the extended classical syllogistic. There is a sound and refutation complete syllogistic system for the relational syllogistic. However, there is no sound and complete syllogistic system for the relational syllogistic. And finally, there is no sound and refutation complete syllogistic system for the extended relational syllogistic.